it's a routing protocol. It's the control protocol that routers are running in order to decide what paths we have to take. Once you've decided what your paths are, you create that forwarding table that we've been talking about. You push that forwarding table into the router, and now packets are coming in, and you're just looking it up in the forwarding table and saying, where do I go? So think of IP, what we're talking about is a packet coming in has an IP header. The router is going to process that packet and send it on its way. So this is kind of the data plane of the network. So these packets are packets that your laptop is sending, that my phone are sending. BGP is a special protocol that only the routers are running to compute what these forwarding tables should look like. Right? So that's the control plane of the network. We're now in the data plane of the network. Good question. Any other questions? Okay, so moving on, next task is we've gotten the packet through the routers. We have all the information we need to get packets through the routers. We've now reached the destination end host. And we said that our task was to tell the end host how to handle this packet. Just a reminder, because it's been a while, what does that protocol stack look like at the end host? Remember, the end host implements all layers, starting from the physical layer all the way up to the application. When you receive a packet, it's traveling up from the physical layer on its way to the application. Okay, so we're at the stage where that IP packet has reached the IP implementation or the network layer implementation in your operating system. What information do I have to provide the destination so that it knows what to do with it next? Right, so my packet's made it up. It's here. What is its next stop along this journey to the application? Is it TCP or UDP? I need something in the IP header that tells me what the next protocol above is. Like, was this a TCP packet? Then I'm going to send it to be processed by the TCP portion of the layer 4 implementation at the end host. Was it a UDP packet? I'm going to send it to the UDP implementation. So it's kind of a demuxing. It's a field that tells you above the IP layer, above the network layer, how do I demux the packet on its way towards the application? And we're going to be demuxing again. When we talk about transport layer design, we're going to have different fields to demux to tell you which application to go to. Is this a Skype packet? Is this a browser packet? And so on. So in practice, the most common protocol field that you're going to see is TCP, because that's by far the most commonly deployed transport protocol. That's a value of 6. UDP is second. We are going to talk about TCP and UDP in a few weeks. So if this doesn't make a whole lot of sense now, don't worry about it. It's a protocol field to tell me where in the layer 4 stack I should go. Okay? And then finally get a response back to the source. I need one field. That's going to be the source address. We already needed it for routers to send back error messages to the source. We're also going to have it so that the destination can respond to the packet it received. Okay, so with that, I think we have all of the information we need. Any questions? No? Okay, so what does the IP packet actually look like? So to parse a packet, we have a 4-bit version number. We have 4 bits that indicate the header length. Because there are only 4 bits, we count header length in units of 32 bits. This is a detail. Total length of the packet, 16 bits. We have a 32-bit destination IP address. We have, in order to handle problems, we have a time to live. We have a header checksum. We also then, for special handling, have 8 bits that indicate type of service, which by and large today means congestion, notification, and priorities. Options, if there are any. As the name suggests, it's optional. If you don't have options, your header is just 20 bytes, the pieces above it. And then a set of bits that we haven't yet dug into for fragmentation. And the protocol field to tell me at the destination end host, am I going to TCP, am I going to UDP, where should you send this packet at the destination? And finally, the source address, so that packets can come back to the source. Any questions before? We're going to look at fragmentation next. Any questions?
How do we handle that source address in the networking layer and not in like the reliable transport layer?
From the viewpoint, so the question is, why do we actually need the source IP address in the header? Strictly from the viewpoint of the destination, I could have put the source IP address anywhere else. You could have put it in the TCP header, in the application layer header, and you would have known where to go find it. Remember we talked about routers wanting to send error messages back to the source? So that's one reason why you want it in the network header. The other is, I think, just convenience. It's hard to imagine communication where you don't have a source that you're going to respond to, so it's convenient to stick it there. Any other questions? Okay. So let's look at fragmentation now. So recap again, every link has an MTU field. This is the maximum number of bits that link can carry as one unit. A router, when it receives a packet that exceeds the link's MTU, is going to split it up. And then you're going to reassemble it at the original, reassemble those what we call fragments into the original packet somewhere in the network later. So what this looks like, let's say you had a 4,000 byte packet that's crossing a link here with a 1,500 byte MTU. My 4,000 byte packet, let's say we don't have any options, so we have a 20 byte IP header, and the remaining bytes are all the payload. What fragmentation is going to mean in this case is that I split it up. I take that payload, I chunk it up into fragments such that that chunk of the payload plus the 20 byte IP header is not going to exceed 1,500 bytes. Okay, so just to repeat that, I take all the non-header bytes and I divide it up. I'm going to have to add an IP header to each fragment, right? Because if I don't add that IP header to each fragment, what's the next hop router going to do with a fragment that has no IP header? So we're going to have an IP header for each fragment, and we're going to put as many bytes as we want here, not exceeding in total the MTU. Is that clear, the goal of fragmentation? Yeah. Why reassemble it? Why do I have to reassemble? Why can't I just send all of the fragments directly up to the application? Just treat them as independent IP packets. Yep. Yeah, the application is not going to know what to do with it. And the reason for that is if you take the original packet, remember we talked about how you add headers. You start with an application layer header, you add a transport header, and then you add a network layer header. So the first 20 bytes are the network layer header. If I just chunked it up like this and I send it along, the network has no problem. Every router along the way, as long as it's seeing the IP header, it knows what to do with the packet and send it on. But if I sent these to the end host and I sent this individual piece of data up to the application, this piece of chunk of bytes here has lost the TCP header and the application layer header, so it doesn't know what to do with that chunk of bytes. I need to reassemble it to look like the original packet before I can send it up to TCP. Right? So for example, think of if I sent this up to the TCP stack, all the TCP metadata is lost. I've lost the TCP header. So you wouldn't know, TCP wouldn't even know if it is a TCP packet. So we're going to take this original packet, fragment it into multiple IP packets, and then reassemble them into what looks like the original IP packet and send it up to layer 4 and the applications above. All right? So you have to reassemble packets or fragments before you can send it up to layer 4 and above. So a few things to think about here is where do you want to do that reassembly? Okay, that's one question we're going to have to address. You have to deal with the possibility that fragments can get lost. They can follow different paths. They can be reordered, and fragments can get fragmented again. So if I hit a link that had an MTU of 1,000 bytes, so I chunked it up into 1,000 byte packets, and then I sent it on, and I hit a link with 200 byte MTU. I'm going to have to refragment that again. So where should reassembly happen? Let's deal with that first. In this context here, I have a host A sending 1,000 bytes to host B, and I'm going through 3 links where the MTU is 1,000 bytes, 500 bytes, and then 1,000 bytes again. when the packet reaches the router R1, it's going to fragment it into two 500-byte packets and send them along. I now have two options here. I can either do that reassembly at router R2, so it's going to reassemble it into a 1,000-byte packet and send it on. Or the other option is that I just send those two fragments all the way to the destination, and the operating system, the IP implementation in the destination end host is going to do the reassembly. Which one do you think we should do? A hint here is think of the end-to-end principle. Packets can take different paths, so that certainly constrains me to two possibilities for where I can do reassembly. I could do reassembly at the router that's at the other end of the link, or I can do reassembly at the destination. Doing it at some other router that's further downstream, not at the other end of the link, is basically not an option, because if fragments take different paths, you can't guarantee that any router is going to see all of those fragments. You can guarantee that the router on the other end of the link is going to see all the fragments, unless they're lost, right? So between my router on the other end of the link and the destination, which one would you choose? Any? Yep. The end host should do it. Why? Yeah, exactly. That doing it at the next hop router, especially if you have a large number of packets that are being fragmented, this is a pretty high burden to place on that next hop router. Right? It has to remember what's involved in reassembly. You have to hold on to these fragments. You have to take all the payload portions out. You have to create a new packet, recompute an IP header, and send it back out. Okay? On the other hand, any other router on the path wouldn't even work because fragments may take different paths. And so there's little benefit but a very high cost for implementing reassembly in the network. And so classic case of end-to-end principle, we say it is sufficient to do reassembly at the end host. It's not necessary. You could have done it at your next hop router, but it is sufficient to do it at the end host. And doing it at the end host keeps a lot of complexity out of the network. So routers are not going to reassemble fragments. We're going to let the end host do that. So quick exercise in designing fragmentation. This is a nice example of actually an implementation done right. So think about how you would design a fragmentation scheme. So in particular, what this means is think of what bits in the IP header you're going to need in order to support fragmentation and reassembly. Okay? So tell me how many fields you need, what are they, and why, and try doing this without peeking at the answer because it's much more fun that way. As a hint, there are really 3 fields you need, 3 pieces of information. Take 1 minute to think about it, and then